everyone. So, yeah, my name is Tomáš Sušánka. I'm the CTO of a company called Trezor. We made hardware wallets that store Bitcoin and other cryptocurrencies. Just curious, who of you in the audience knows Trezor? OK, wow, a lot of people. So you might actually know that just on Tuesday we launched a new product. So yeah, just if you want to check it out later. I'm also saying that I might get a little bit rusty because this week and the previous one was kind of crazy. But I'll do my best, explaining this a little bit difficult topic. So let's get into it. So yeah, quantum computers, quantum computing, and all that. Alternative title, apologies, let me just turn off and on this thingy. Wow, there you go. Yeah, alternative title is what the hell is this, right, in the polite version, because the whole topic is super difficult and kind of weird and counterintuitive, but we will try to explain it in a manner that's reasonable, but this guy on the picture is going to help us quite often. So first of all, let me share a few words about quantum computers and the quantum shenanigans first. So disclaimer, I'm no quantum physicist. I'm not a regular one either. So I'm not the guy that would explain any of that. I provided I'm going to share a QR code at the end, and there is a nice video that kind of explains the basic of the quantum physics behind it. So I encourage everyone to check it out later on. It is very weird, cringe, and the quality of the video is like 5 pixels to 5 pixels. So take it with a grain of salt, but it nicely explains the basic. For this talk, we're just gonna, stick with just a very high-level explanation, where basically the quantum physics are based on this double-slit experiment, which is showing the image on the side, which basically proved that light and matter can behave both like particles and waves. Yeah, I mean, I probably haven't really explained it at all. This is really a huge rabbit hole, and I encourage to consult your favorite ChatGPT tool or whatever on that topic, because that's something we would need another talk for later. So for now, we're just going to stick with what quantum computers are. Quantum computers, are computers that are using this quantum physics to achieve something that's not possible on traditional computers. So, as you know, in traditional computers, we have this 0, 0, and 1 bits, right? And it's either 0 or 1, like that. That's it. And that's the basics of all the computing that you can, think of, because it's really that simple, right? Like either it's 0 or it's 1, and that's basically it. In quantum computers, it gets a little bit weird. You can have 0, 1, or something in between. And something in between is not accurate. It is actually 0 or 1 or both at the same time, right? Which is very counterintuitive, and it's probably something that's puzzling you already. We call those qubits. So as you have bits, then you have qubits as quantum bits. And you can build these computers using a special dedicated device that are using this quantum physics as the underlying phenomenon. There's also how we denote that, but that's not important. First, before we go further, I also want to clear two terminologies, or two terms. First of all is the superposition. So superposition is the state, or just the ability to have multiple states of the quantum computer before you actually measure it and you can have a look at the final results, right? Similarly, coherence is just the stability of the whole system, right? So quantum computers are very difficult to build, but they are also very difficult to maintain, right? Like to keep the state in the quantum state. The thing is that once you have just a little bit of noise, and I don't mean someone screaming, there's just like some photon flying around or anything, it can basically break the whole system, and then it collapses, right? In the sense of that it collapses to a traditional computer and not the quantum one. this guy again. What is important to say is that quantum computers, cannot magically solve everything and are not faster to each and every problem, right? I think that's sometimes quite common in popular literature or wherever, that quantum computers would solve everything magically faster. No, it's not the case. What they can do is that there are specific algorithms that are designed for quantum computers, and on quantum computers, they can solve certain problems in extremely more effective way than on the traditional computers, right? So I just want to say that not for every problem quantum computer needs to be faster, but there are problems that quantum computers are faster in. And one of such algorithms is so-called Shor's algorithm, which is already from 1994, which basically showed an algorithm on a quantum computer how to break the discrete logarithm problem. Break is not the correct word. The correct word would be, it found a way how to solve the problem in a polynomial time instead of, what was it? Exponential, thank you. So yeah, already in 1994, which is, by the way, kind of amazing, because at that time, no one really knew whether quantum computers are a feasible thing. We kind of still don't know that, but there are quite some advancements. And it was kind of amazing. And why is this very important is that the discrete logarithm problem, is the basics of a lot of cryptography, right? And cryptography is something that we are using everywhere. Like it's internet, Bitcoin, e-commerce, software as a general, banking, army stuff, governments, like really a lot of fields. And that's basically the scary thing about that if someone would have so-called cryptographically relevant quantum computer, meaning a quantum computer strong enough, they could actually break this cryptography, right? So that's the basics of the Shor's algorithm. Now, I want to talk now more about the current state of things, right? Because now, so far, it was very high level and theoretical. But let's have a look at the current state of things. So I was at a conference about 6 or 7 years ago, and there was a talk from some of the renowned cryptographer. And I really liked how he described it. He had one slide where he had "don't panic," and he was basically saying quantum computers are still very far away. We are not there at all. Maintaining the coherence, the superposition of all that is extremely difficult. It's really the quantum computers are always have to be super cold in one of those types how to build them. It's very extreme conditions how to even build them. It's very complex, and we don't really have relevant quantum computers as of today. We need millions of qubits. We currently have tens or hundreds, right? And I don't mean thousands or millions. I mean like 100. Like that's it. You probably saw an article just yesterday from Google. So they have this Willow chip, and this one has 105 qubits, right? To do anything relevant against cryptography, you need millions, right? So I just want to illustrate that we don't have to panic because we're just not there yet. That being said, the consequences of such such event happening, meaning someone would have a quantum computer, are enormous, right? It is something that would really break the internet and the modern society to some extent, and the impact is simply huge and should not be underestimated. This was, by the way, a talk, as I've mentioned, that was 7 years ago. And if you would ask me personally 7 years ago or 10 years ago, I kind of thought that this is some science fiction, that like, OK, quantum computers, it's a nice buzzword and all that. But I thought it's sci-fi, and I'm not going to be alive to witness that. But in the past 5 years, there's really quite some scientific advancements in the field. I'm not saying it's going to come next year, but I think we're going to witness it in our lives, which I haven't believed before. So it's kind of amazing. So in other words, a summary. The good news is that there isn't a quantum computer, and it will take some time, right? It is not around the corner just yet. The bad news is that it can break everything, as I've mentioned several times already. You might be wondering, what is the sometime, right? So what is the estimate when the quantum computers could actually come? I like this chart from an article that basically they've asked a number of researchers and industry experts on the topic, and they basically asked, hey, so when do you think we're gonna have a quantum computer that is able to break some cryptography? And you can see that 5 years, it was just a few, but like 20, 25 years, like there was, the percentage was quite high. I mean, this is just like subjective opinions of some people. The fact that you put it together and put it on a chart doesn't make it objective. It's still some subjective opinions of some researchers. But it gives you, an interesting idea what the best people on the topic actually think. And, it's quite amazing that in 20 years we could actually have a cryptographically relevant or just relevant in general quantum computer. And this brings us to the topic of post-quantum algorithms. So post-quantum algorithms are algorithms that are run on a traditional computers, meaning on your normal computers that you might have. But they are not vulnerable to the quantum computers. They are not vulnerable to the Shor's algorithm that I've mentioned 10 minutes ago, right? So again, these are not algorithms that would run on the quantum computer. These are algorithms that are running on the traditional computers, and they are not vulnerable to these attacks on the quantum computers. NIST, the National Institution for Standardization, American institution, is running a competition since 2016. That's basically, they're just calling all the best researchers from all around the world to submit their ideas on post-quantum algorithms. And just last year, because these things take a very long time, just last year they standardized the first 3 algorithms. And they are actually now, there's another like sub-competition running now. And they want to standardize one more. But what I'm trying to say by this is that we already do have standardized post-quantum algorithms that you can use, and anyone can use, obviously. NIST also mentioned that they would like to deprecate the traditional cryptography schemes by 2035, which, to be honest, kind of surprised me, because it's 10 years away, which is very close by, I would say, right? Like 10 years, that's nothing in the world. So that's kind of interesting, kind of scary as well, because that's something that we'll have to tackle as a community. That being said, obviously, they are giving this recommendation for governments and army and whatever. It probably, doesn't have to concern each and every website on the internet, but it is quite interesting that they are, they start to push this really, really hard. There are basically 2 types of these algorithms. There is the key exchange, when you're trying, to exchange a key with some second party, and then there are these digital signatures. The good news is that there are good key exchange algorithms, but there isn't an all-around good algorithm for digital signatures just yet. Now you're probably thinking, so what's good and what's bad, right? So there is this nice table from Cloudflare. Cloudflare has a nice summary on the algorithms. Again, links at the end. And you can basically have a look so the first one are the traditional algorithms, right? So the first and the second, that's the usual cryptography that we have. RSA is from the 70s. At 25519 is, I don't know, 2000, give or take, 90s maybe. Yeah, don't give me my word for it, but it's old algorithms that are already here for quite some time. We're happy with them. They work great. As you can see, the first one, small public keys, small signatures, quick signing, fast verification, all that. Awesome, right? That's why you basically see the ED 25519 or the EC DSA, doesn't really matter. They are everywhere, right? They are in Bitcoin, they are in HTTPS, they are really all over the place. Now, if I go to those post-quantum ones, which is these ones, you can see that suddenly the table is not that green, right? Unfortunately, there are some that the public keys are quite small, but then the signature is huge, which depending on your setup can be and also doesn't have to be a problem. It really depends. And then again, the CPU time, right? Like, so for example, SLH DSA takes quite some time to sign, right? But it's quite fast in verification. Like, again, if you're making a signature once a month, it doesn't really matter. But if you need to do it, each second, like really millions of them, now it's obviously becoming a problem. And yeah, there is just a small add for Trezor. We are actually using these two algorithms in our new Trezor Safe 7, but I'm going to talk about it at the end, so I don't want to confuse you now even more. So what I just want you, to take from this slide is that key exchange good, digital signature still something to research and discuss. We're going to now have a look at the two fields of, that I believe are concerned the most, or I believe could be the most interest for you. It's the internet, obviously, and then Bitcoin. So let's start with the internet. So good news first. The adoption is already happening, and you might not even know about that, right? Because everything is happening under the hood. Cloudflare is doing quite some job in that field because they already they have it turned on by default. And in case your browser, whatever it is, supports those algorithms, they're gonna use the post-quantum algorithms in your HTTPS connection. So without you even knowing that, you are probably communicating with a lot of websites already in the quantum-safe manner, in case the website, is using Cloudflare, or there are, of course, also other providers. But what is kind of interesting is that it's about 41%. But there is like a toggle on the side, and if you exclude bots, because they have like a toggle where you can enable or exclude bots. If you exclude bots, then meaning it's only humans, or should be, it goes like to around 49 or 50. So the adoption is quite happening. So it's pretty cool. And also a note, Cloudflare is almost 20% of all internet websites, so they're quite. Do you know what Cloudflare is? I suppose, right? It's like a CDN provider, network stuff, and all that. I just wanted to say here that it's almost 20% of all internet websites, but that doesn't imply 20% of all internet traffic, because they have a lot of smaller websites. So. It's not 20% of internet traffic, right? The number is different, but it is 20% of internet website. So kind of interesting, and Cloudflare, I believe, is doing a lot of great stuff in this area, and there are some articles later on. In general, what is the problem with the internet as a whole is that it's a very diverse environment, right? Of course, you have browsers, but you have also this whole public key infrastructure, HSMs, like those devices like hardware, software modules, all kinds of logs. I like this. I put this sentence, and every server admin that cobbles together a script, because that's from another talk that I was looking at, because that kind of summarizes it well, right? Like it's a huge. Even if I say internet, it's like, OK, like what do you mean, right? Like which part? Because it's so omnipresent, and it's really something that is big. So the main problem also with the internet is that you have this certificate chains, right? Like when you do HTTPS connection, you receive a certificate, and this certificate is signed by another certificate, and that certificate is signed by some authority. And you would have to, apply all those post-quantum signatures to those certificates to make the whole thing quantum safe, right? Which sounds pretty easy, and it's something we can do. But basically, there are two problems. So first of all, as I've mentioned at the beginning, like we do not have all-around great digital signature, right? Like this signature suddenly grew from 64 bytes to whatever this number is, right? Like suddenly the signatures are way, way bigger. So this can be a problem because when it adds up, it basically, suddenly you're not transferring just a few hundreds of bytes, or let's say 1 kilobyte, but suddenly, you're adding way more data inside the handshake, meaning, you're slowing everything down. That's basically the last point that to make it quantum safe, to add all of these post-quantum algorithms, I think it was Google measured that it would, that you would need 7 extra kilobytes, right? It is something we can do, but that being said, quantum computers, again, are not around the corner right away, so it probably doesn't make sense to add it just right away. But it's great that we have it ready. There is also this term protocol ossification. I'm not sure if you're familiar with that. That basically says that you have some kind of protocols that are designed in some way. So, for example, HTTPS or the underlying TLS, for example, they say the handshake can have at maximum 10 kilobytes. I'm making that up, okay, but just to illustrate. Let's say the specifications say it can have at most 10 kilobytes. But so far, it was only 1 kilobyte, right? So no one really cared. And when some people were developing some libraries, and so they just put an arbitrary limit of 2 kilobytes because there was, like, why not, right? There was never, ever was anything bigger, right? And this exactly, kind of things along the way can hurt us, right? It can be routers, it can be some manufacturers, HSM manufacturers, browsers. Again, like it's really everywhere. So this can be a problem as well, and it takes quite some time to fix these. So now I'm getting into the cryptocurrency part. So I'm going to talk mostly about Bitcoin, but this applies to any of your favorite cryptocurrency, most likely as well. In a nutshell, Bitcoin is not currently ready for the quantum threat, for the quantum computers. There are two threats, basically, if I again simplify things. So first, we have these Bitcoins at rest. What I mean by that is that these are Bitcoins that are already mined. They are already in the blockchain, and they are there for, they can be there for years, right? Like they are already mined, and they are in the blockchain. I'm going to talk about that first. So the biggest problem here is, and I don't know how familiar you are with Bitcoin, so I'm going to use some terms, so I hope it's understandable. But the biggest problem here are addresses that reveal their public key. Again, like this is kind of where it gets difficult, but in Bitcoin you have more types of addresses, and in some addresses these public keys are then hashed, so they are not visible until you spend them. But a few years ago, or at the beginning, we didn't do this. We didn't hash the public key. So meaning the public key is visible on the blockchain. So what this means is that if anyone has a quantum computer, in case anyone in the audience has one, what you can do tomorrow or today, you can have a look at the blockchain, and you can select the public key. And then you can, using the quantum computer, using the Shor's algorithm that we talked about at the beginning, you can basically derive the private key, and then using the private key, you can spend these coins, right? So this is definitely a big threat for Bitcoin. And there are about, like there's an estimate, there are about at least, probably more, 4 million of Bitcoins that have the public key available. It's usually those coins from Satoshi Nakamoto, the inventor, from the beginning, right? Because these were never spent, so they just lie around there, and they are basically vulnerable to this. And then there is the second problem, which I call Bitcoin in flight, which means those are transactions that are not already in the blockchain but are about to be mined, right? So that's basically if I would just put together a transaction now, I would send it to the network, then the average or the median of the transaction being mined is around 10 minutes in Bitcoin. So again, this is the time that I need to reveal the public key, meaning someone again can attack it. So luckily, the discussion is slowly picking up. I think, again, as I've said at the beginning, the don't panic and panic exactly applies here. I don't think it's something that's going to happen tomorrow, but I think we as a community should get ready. In Bitcoin, everything takes ages. It's a very conservative piece of software, which is a good thing, right? By design, because of the huge value there is. But I'm glad that we're starting to having this discussion because it's going to take another 5 years at least, to actually agree on something within the community. Because as Bitcoin is, decentralized, then of course it also has, this part when you have to make some decision in a decentralized way, which is, sometimes hard. There is this BIP 360. By the way, I had, in case you know Bitcoinový kanál, the YouTuber Kitsom, I was there as a guest half a year ago. I talk about BIP 360. Has anyone saw that by any chance? OK, good, because the whole thing that I've said there is no longer true, because they basically rewrote the whole thing. So what I'm trying to say is that this is something that is under heavy discussion and development. I've realized that I haven't said what a BIP is. So BIP is Bitcoin Improvement Proposal. It's basically a document that is trying to describe changes that would be implemented inside the network. And the idea behind this BIP and the following one is basically to introduce new addresses where there are going to be a post-quantum signature on top of that, again, meaning that you don't have to, the quantum computer cannot attack these because these should be safe. It's a very slow discussion. It's going to take ages, but I'm glad that we're starting to have this discussion. There are also a few very interesting caveats or issues with that. And first of all, it is that everyone will need to migrate to these new Bitcoin addresses, right? So in case anyone from you has some Bitcoin, you have it on a traditional address, and you personally, for example, using our hardware wallet or using any wallet, you will have to take them and send them over to a different post-quantum address, right? In other words, it means that you need to do something as a user. We cannot transition it for you because we do not have your private keys, obviously. This is going to take quite some time. So it's kind of, we need the community participation or the users' participation on that. Secondly, what are we going to do with coins, with Bitcoin, that is most likely lost, right? Because, for example, those Satoshi coins, that's about 1 million of Bitcoins that was mined in 2012, 11, I don't know, ages ago, and they've never been spent. And you could assume that the person that was holding them at some time no longer has the private key to access them. So they cannot really send them to another address because it's just impossible, right? And basically, there you have two options. So as a community, you have two options. So first of all, you're just going to say, OK, so whoever has a quantum computer strong enough, here's a present for you, and just take them, because that's the market maximalism that just, if you build a quantum computer, I guess you deserve it, and just here you go. That being said, again, it's more than 4 million of Bitcoin. In total, there is 21 million of Bitcoin. It's probably going to hurt the price and the Bitcoin itself a lot, right? So is that a good idea? Not really sure. Or you have the second option where you just say, OK, you have 5 years or whatever to move these coins to new addresses. If you don't do it by the time, we're just going to make those coins invalid, right? Like burn them, basically, or just say, hey, these are no longer valid. Which sounds easy, but to some degree, it it is against the philosophy of Bitcoin to some extent, right? Like it's not really cool to forbid this. That being said, it's a hard question that we'll have to tackle in the following years. There are good arguments for both pro and against. And by the way, also, like, it concerns the Satoshi coins, but there are also examples from today's world, right? I don't know if you know the poor guy, I think he's from UK, where he threw out a disk, a hardware drive, about 5 years ago. Like, he threw it into a garbage. And, you know, he's trying to get the disk ever since. And he wanted even to buy the piece of land where they're doing the recycling and all that, but the town, forbid it. I'm going off track, but what I'm trying to say, like, this is exactly the example as well, right? I mean, he cannot send over the coins. He doesn't have the private keys anymore. So it's a really interesting puzzle what we should do about these coins. And lastly, yeah, if there is a, if someone really has a strong quantum computer, there's probably not that big of a difference whether you're attacking the ones that are in the blockchain or the ones to be mined, but that's, yeah, very Bitcoin heavy, so we don't have to dive deep into that. Yeah, lastly, I just wanted to say that, we at Trezor, so again, we're doing a hardware wallet. We cannot really make a quantum safe hardware wallet because the Bitcoin and cryptocurrencies are not quantum safe themselves, right? So it doesn't make sense. No one would attack your Trezor. They would attack the blockchain itself, right? It just doesn't make sense. But that being said, we wanted to do, something to get ready. So at least what we're doing is that we are signing the bootloader, the tiny piece of code that is inside the device. We're signing it with the SLH DSA. And then we're also providing a certificate inside the device that is proving the genuinity of the device. And we're signing that with ML DSA. And basically, this allows us that once the threat is imminent, in 5 years or 10 years, and when Bitcoin adopts these changes, we can basically send them to the device in a quantum safe manner. Again, you might be wondering, like, why there are two. Like, again, just remember the green and red table that I shared. They have different properties. So, for example, SLH DSA, it really takes a long time to generate the signature. But that's OK for us because we sign the bootloader. We release new bootloader twice a year or something like that. So it doesn't really matter, that it takes quite some time. But the important thing is that the verification is fast. So every time you turn up your Trezor, there's actually verification of this algorithm, and the verification is fast. So we're OK. And then there is the MLDSA, which, on the other hand, has different properties, and it's the size of the signature is smaller. Yeah, anyway, so it has different properties, and it was more suitable for the certificate. So again, like, I think it's great to check out the article from Cloudflare because it says, it is able to give you an idea about like which are the correct ones. As you can see, MLDSA, yeah, the table doesn't really say it all because on top of that, SLH DSA is based on the hash algorithms, which are believed to be more secure or more proven by time. MLDSA is based on the lattice cryptography, if I'm not mistaken, so which is kind of new and not proven by time. There's a lot of things, to take into account when you're deciding which ones you should take. OK, thank you. That's it. OK. I also have a QR code just at the end. Maybe if we could show just that for just 1 second. So can we just swap back to the computer? Yeah, just if anyone wants to, this is a link to the Notion, to my personal Notion, when there are links and further reading and the slides and all that. So just if you want to have a look. OK.
It's for questions. Literally a few minutes. You can either use the Slido, or if you want a mic, I can come and hand you a mic if you're feeling brave. Up to you. I know very little about things like you were talking about, and I now feel even stupider than I felt before. When you have speakers who are so into what they do, I think it's fascinating and incredible. But now I realize I know even less than I thought I knew. So thank you for that. Which,
by the way, applies for me as well and for everyone, because the deeper you go into the rabbit hole, you are more confused. But that's like with everything, right?
Any questions? Who's got some burning questions for Tomáš? Yay, nay? Yes! Would you like a microphone? Let's give you a microphone. Super stuff. Should be on?
It's a mic.
Microphone is on? That's all right.
1, 2, 3, yes. Hi, thank you for the presentation. I was curious, you said quantum computing is the biggest threat right now to the blockchain, or let's say even to Trezor, that you're not proofed from quantum computers. But do you mind sharing, not into too many details, but what are other things, or maybe even cyber threats that you are mostly concerned in Trezor and overall to blockchain? Yep.
Let me maybe split it into two. So first of all, the biggest threat for Bitcoin itself, I indeed think it's the quantum computers, even though it's a long time away. And then is the scaling discussion, because like many people don't really realize that Bitcoin doesn't really scale for 8 billion of people on the planet, right? So it's a completely different topic and has nothing to do with that. But because of the size of the blocks is constrained, you cannot really fit enough transactions, and it's some problem. It leads to centralization, and it's something that we'll have to also look into. So that's with respect to Bitcoin. And then secondly, for Trezor, this applies as well. But then at the end, what I always like to say, it is always the user that is using the device. And I am also thinking that it's our job to make it in a way that the users can use it in a safe manner. Because I like this saying, security at the cost of usability comes at the cost of security. Because when we're not doing a good job for the people to use it well and use it correctly, then they do something stupid and they lose their funds, which unfortunately is happening because they quite often are scammed by phishing websites and all that. So it's not just purely technical side of things, it's also more of a user experience issue. Good.
Okay. We've got time for one more question. There is, there was. Something up on screen. One more question? Yes.
Yes, I got a question about Ethereum because it may be like more complicated to migrate to post-quantum cryptography. You have talked about Bitcoin. Can you say something about Ethereum?
Honestly, it's the same thing. None of those, I mean, there are maybe some very bizarre cryptocurrency projects that are trying to have it, but none of those top 100 or whatever has any post-quantum security whatsoever. So it's something that I think we will see popping up as well. But as far as I know, there is also nothing in Ethereum or Solana or you name it. I think it's going to come in the following years.
There are other questions, but we are on time. But hopefully you can grab Tomáš afterwards. But another round of applause for Tomáš.
Thank you.